Okay, so our first speaker this morning, our invited talk is by Polsterer on from photometric redshifts to improve weather forecasts and interdisciplinary view on machine learning in astronomy. Kai comes to us from HITS in Germany, and he's has this interesting background of physics, astronomy, computer science, and building instrumentation, or working on instrumentation. So he's done a lot of different things. And now he's really our guru on machine learning. So you can take it away, Kai.
Yeah, many thanks, Jessica, for this very warm introduction. And as you can see, yeah, it's a little bit frustrating not to be in Granada, but I thought to make the best out of it and invested travel money in a professional video team supporting me. So Brennex Films now realizes the presentation of me today. So first of all, good morning, good afternoon, good night, and good day to everyone listening. Yes, it's many time zones we are bridging, and it's definitely different times and difficult times with Corona being around, but I seriously hope we will meet soon again. So when I was invited to give a talk at ADAS, I was really happy. When I heard it's going to be virtual, I was a little bit of upset, I must say. But seeing how much effort was put in the presentation and preparation of the presentations online and how well we were trained on the presentations, I really have to thank a lot to the local organizing team as well as the program organizing team making ADAS happen in a virtual way. And I will especially have to thank them after the conference because I think it will be the best virtual conference of this year. So yeah, today I want to talk a little bit about photometric redshift estimation and how this helps to improve weather forecast. I thought it's good to give a more interdisciplinary view on what actually combines different sciences. And it's machine learning, it's methodology that is similar to many different fields. So whatever we do, we often have to think of what is the use case we are talking about, and there are connecting bridges if you think about what are the methods you apply to your data. So in this example, I'm talking about supermassive black holes on one side, because those are the sources we want to observe in a photometric way, where we want to estimate redshifts photometrically. Those are supermassive black holes, and they are accreting material, and thereby they are amongst the brightest sources in the universe. That allows us to observe them at really large distances, and this allows us to get insights into the early universe. But how does this connect to weather on Earth? There might be probably some relations, but the relations here lie all in the methods we apply. So let's talk about what you always have to talk about when you talk about machine learning. Do we actually have too much data? And what is the solution if we have a lot of data? So what kind of data do we have? At the moment, we already have Gaia. That's something like a petabyte of data. The mission is still flying and it's collecting a lot of data. But we also have not only missions in space and instrumentation on Earth, we also have simulations. And the illustrious simulation, for example, delivered also a petabyte of data. And if you think about the upcoming SKA, yeah, it will be 1 billion gigabyte, an exabyte per day. So we are really talking a lot of about a lot of data. And what we need to deal with it is another way of analysis. Machine learning actually could be key to improving the way of analyzing the data. We can take away the necessity to do things manually, where we actually could use computers and train computers to assist us. But how do we do so? Yeah, one typical problem we are facing is solving regression problems. By looking now at this equation, you see it's something very simple. But what we want to do actually is we take a large catalog, and from the catalog, as you see in the equation, yeah, we sort of have our model. We build our model. This is our regression model that helps us doing the analysis. In our regression model, we put our features. This is the data we collected through our catalogs, our surveys. And what we want to do, we want to predict values. Values we want to use for a scientific analysis. Those values could be of different kinds. In this example, I'm doing regression of real values. So in the example I was talking about, it's about estimating the redshift of a source. What is redshift? So people often combine or compare redshift to something like the Doppler shift. That's not the right picture, because while light is traveling through the universe expands, and thereby the wavelength gets extended. This is a so-called redshift. And as you can see on the equation, in the equation you see how the wavelength, the rest frame wavelength is compared to the observed wavelength, and this gives you actually the redshift. In this example, you see two spectra of two different quasars. Okay, so yes, the photometric redshift estimation we spoke about. What you see is what we need training data is essential in principle. If you want to do machine learning, you need training data. In this example, you see a plot of the spectra taken in the quasar spectra taken in Sloan in an early data release 3. And what you can see is distinct lines moving through the different wavelengths. So you see the Lyme alpha, you see the magnesium line, you see all the different lines as they slowly move from a low redshift at 4,000 angstrom to a higher redshift at 9,000 angstrom. So photometric redshift estimation is not complicated. I spoke about it at different ADASs in the past. So if you use a simple k-nearest neighbor model, this is by looking at certain features, looking how certain sources look like in the high dimensional feature space, you can select objects in the vicinity of a source just by comparing them feature-wise. Those with similar features appear to have the same physical mechanisms. So by just calculating the mean over objects in their vicinity, you can estimate a regression. So what we put in the past were magnitudes. Magnitudes in principle are taken in Sloan as point spread function magnitudes, also model magnitudes that are the best out of the Dever-Couleur fit or search profile fit. And what we got out were redshifts. So data in, training a model, predicting redshifts as a regression task. Crucial when you do machine learning is the question of how do you evaluate performance. So there are many different scoring functions. You take the root mean square error to compare your estimated value with actually the true value of a source determined in a spectroscopic way. You calculate something like median absolute deviation. You look at biases, standard deviation, max errors, mean errors. You look at how much they spread. You look at a lot of different values in there to estimate actually how bad the error is. And you have a lot of multiple diagnostic tools actually to look at the data in a visual way. And in this plot on the right-hand side, you see the spectroscopic redshift that's considered the true redshift being plotted against the photometrically estimated redshift. Here in this example, I used the k-nearest neighbor model with the 7 nearest neighbors being considered for the estimation. And as you can see, the perfect result would be a direct line going through the diagonal. There are some errors in there. But the question is, what about uncertainties? What we need to take care about are uncertainties, because being uncertain about certain things helps us to be more precise. You will see in a second what I mean with this. So we have uncertainties in our model. They come from, do we have a representative data set for training? Do we actually have the right algorithm chosen? Is it able to generalize well to the problem at hand? A lot of different things are here to be considered as model uncertainties. We have input uncertainties, measurement errors that occur while doing our experiments. And those input uncertainties, of course, influence how good we can and how precisely we can estimate a certain value. And therefore, we should have uncertain estimates. If you now take your model uncertainty, your input uncertainty, and your uncertain estimates you want to produce, you are taking the step going from predicting a single redshift, in this example, a redshift of 0.1234, and you want to go to something like a probability density function where you actually predict a probability density that tells you how likely it is for a given redshift that this redshift is a correct redshift you want to have. Probability density function have a lot of nice side effects. So If you represent your result as a probability density function, you can take two distinct values, A and B, and you can just estimate or calculate what is the likelihood given a value of A, given a value of B, or by just integrating over the probability density function, you get a probability out. You really can estimate how probable it is to a certain percentage that something is in between a certain range. And that makes your science stronger, because now you can say, not only give me quasars with a high redshift, you can say, give me those quasars with a redshift above 5 that have a probability of being above 5 of more than 90%. And that makes you more precise in the way you analyze and the way you inspect your data. The challenge here is multimodalities. What you see in the plot is at the upper edge, the individual values, redshift values of the nearest neighbors with respect to the photometric features. And at the lower bar, you see a histogram that tells you what are the frequencies of certain values happening. And what you see now is the true redshift is a red line somewhere around 2, but you see there are 2 peaks. We have a multimodality. So our model, a nearest neighbor model, would say our source is either something around 0.5 or something around 2, but nothing in the middle. Evaluation tools, as I said, are very important. But what do you do if you have such a multimodality? The root mean square error is a proper score, but it's in the middle of 2 peaks. In this example, I plotted 2 peaks. One peak is perfectly aligned to the true redshift of 3.45 of that example. The other peak is at a different place. But if the data doesn't allow you to clearly state it's either A or B, you have to be able to give it a soft answer. In this example, it's saying it's A or B. But if you now take the root mean square error, you're looking at a value in the middle. And as you can see, the likelihood is really small at that point. So you don't take the shape and the overall structure of your probability density function into account. You're just condensing it down to a single value. So the question here is really, is this a proper tool for analysis? Another thing I see quite often is that people start stacking PDFs. In this example, on the left-hand side, you see very narrow and precise estimates. It's like saying tomorrow is the temperature 15 degrees plus minus 0.0001. You all would know I'm lying at you because I cannot precisely predict the temperature of the next day. So it's lying at you. But if you now start stacking them and define outliers to be outside of a certain area, you see in the plots above that the likelihood is close to 0. And in the example further to the right, the likelihood is increasingly higher, but the overall result tells you there are a lot of outliers. That's not true if you have multimodalities. So the question is really stacking PDFs. Is this the right way to evaluate? So back then, when we were working on photometric redshift estimation, we came along the continuous rank probability score, the CRPS. And the CRPS is a nice tool that allows you, with a single score, to measure how sharp a prediction is and how well calibrated it is. I show you in a second what this means. So given a probability density function, in this example, the black is a predicted probability density function in the redshift space. And specified is the mu and the sigma of a Gaussian prediction in this example, and the true redshift of 2.2. Then you just take for the CRPS, you transfer the PDF by integrating to each individual value. You transfer the PDF into a cumulative distributive function. And now you can look at the true redshift at z equals 2.2. The true redshift itself turns into the Heaviside step function. And if you now integrate between the Heaviside step function and the CDF of the predicted redshift distribution, the probability density function of the predicted redshift, you get the CRPS. So it's visually quite obvious what you do. So taking all together, now you see the equation is not so complicated. You just take 2 CDFs, the one of the true redshift, the CDF of your prediction, you combine both with each other, and then you integrate over the surface area in between. Another nice tool is a PIT, the probability integral transform. It's a visual tool to actually see how well your predictions are calibrated. If you take the CDF at the upper right and evaluate it for each individual estimate at the true redshift, you get a value between 0 and 1. If you now take those values for all your estimates, you get something, you get a histogram representation. And in this example, the PIT tells you it's underdispersed. So if your predictions are too narrow, as I made the example with temperatures, you always hit zeros and you always hit ones because your estimate is too narrow and the wings of your prediction will never catch, only the wings will be hit. And then you get an underdispersed image of your predictions. You are over dispersed if you would say tomorrow the temperature will be 10 degrees plus minus 30 degrees. You always sort of hit it, and therefore you always hit values somewhere in the middle of the CDF around 0.5. If you're over predicting or under predicting, you get a bias term in, then it's slanted. Only if it's well calibrated, you get a nice line. So now let's apply what I told you about evaluation tools to our example I showed you in the beginning. We use k nearest neighbors on all the quasars in the Sloan Digital Sky Survey. If we now say the mean value of the k in n gives us the mean of a single Gaussian of our probability density function, then the sigma is just an arbitrary value we choose. So saying our uncertainty is 0.01 in our predicted space gives us a horrible PIT. We are completely underdispersed. We are just saying we are absolutely sure about our values, but we are lying about the precision of our uncertainties. Therefore, the CRPS is high as well. If we now say, okay, then our estimate is worse. Let's say we have a single Gaussian with a value of 0.2. We slightly improve, but we are still not telling the truth. And this is what the PIT and the CRPS shows you. If you now take a single Gaussian and calculate a standard deviation over all the nearest neighbors, so you take the nearest neighbors to calculate a mean value, and you use them to calculate a standard deviation, you get an adaptive sigma. And it's improving step by step. And if you compare the results, you see from being lying about uncertainties, making them worse, going to an adaptive sigma, you improve slightly your performance. But it's not correct, because what I told you in the beginning is we have multimodalities in here. And multimodalities mean it's not a single value, it can be multiple values. And what to do about multiple values? We need a different representation. In this example, and as you could see here on the slide, you use a Gaussian mixture model to actually represent your estimates. You take the results of your k nearest neighbors and fit a Gaussian mixture model to allow a multimodal representation. If you do so and use a Gaussian mixture model with 5 components, we use the Ikaike information criterion and the Bayesian information criterion to evaluate a good number. Some people would say 4 is better, some people would say 10, but I say 5 is a good number, and actually it doesn't matter really. But if you look at it, you see, taking the multimodalities into account, the plot completely changes in the way it's representing. Now it's no longer plotting the true redshift against the estimated redshift. It's on the y-axis, it's probability density functions. And so you see a sum probability density. And now from the plot, you can see that redshifts of 0.7 have also a likelihood to be mistaken as redshifts of 2. And this is the multimodality I was talking about. If you now use a random forest, take the individual results of the individual decision trees in your ensemble, and you combine it with a Gaussian mixture model, you have something like a quantile regression forest, you further improve. And as you can see, the PIT becomes more and more evenly calibrated, homogeneously calibrated, and the CRPS is dropping as well. So if you now compare them, we are going further steps. So from single estimates, single Gaussians, to multiple Gaussians. But what is the next step? The next step is talking about learning on images. And here the IVOA is a great help. And I can tell you, besides the trouble I'm having today with computers, and believe me, I'm sweating like crazy with all the problems getting the presentation starting. Last Friday, I was working together with colleagues in medicine. And yes, thanks to all the gods of you who invented FITs, who invented meta information and common standards, I'm freaking out getting TIFF images, and no one can tell me how they observed, what they observed, at what resolution they observed, and there are no logs at all. And then you have a mess of data. We have the International Virtual Observatory Alliance with HEALPIX and HIPS and those tools like HIPS to FITS and HIPS by Thomas Boch is having a nice poster on that, by the way. We now can access all the huge data sets in a uniform way, and we can do deep learning on massive data sets. And that's what we did in the past. This all goes back to work done by Antonio Di Santo while he was doing his PhD thesis with me. So we took a deep convolutional neural network, and at the end, we used a simple mixture density network. A mixture density network is a fully connected network that just takes the learned features out of the deep convolutional part and uses those to predict a set of mu, sigmas, and weights. And those values are actually what you need to define a Gaussian mixture model. So by doing so, we were now able to take images as input and produce a Gaussian mixture model, a PDF as prediction. So when we trained a simple mixture density network just on the pure features, just the later part, taking the photometric features, you see we get nearly a perfectly calibrated PIT, and the CRPS dropped by another order. And now take into account the plot is now showing the log sum probability density. Otherwise, it would look like a tiny line in the center and being very precise about the multimodalities. So this is really showing when using a proper scoring rule, when training a network with a proper scoring rule, you improve your performance tremendously. So what happens if you take images? You further improve it because you now access the full range of photometric features encoded in the images. It's not only that you take the pre-extracted features, it's really that you take all content of information from the image and extract it to build a PDF. And as you had seen now, with proper training and proper uncertainties, you get to much better and honestly calibrated results. So if you take those things now and you want to know my age and you take a picture of myself and a picture of a dead rotten fish, you see the picture of myself tells you my redshift is 1.7, so I'm roughly 10 giga-years old. And the rotten fish is roughly 3.5 giga-years old. And of course, that's correct because a fish doesn't live as long as a human. So it tells us there are a lot of limitations. A network trained to do a certain task cannot be used for a different task. Now let's quickly jump to the weather forecast. How is all the things from photometric redshift estimation of quasars, rotten fish, connected to weather forecasts? In principle, through methodology, as I said. In this example, we took data from the European Center for Medium-Range Weather Forecast. And this is a lot of data. On a dense grid of 81 by 81 cells, you have 18 physical parameters. And now in the weather forecast simulation, you don't run a simulation once, you run it 50 times in order to deal with the uncertainties you have in the input data, you have in the model, to get a better description of what the weather will be next day and whether you are going to have a barbecue next day. So what people do is they do statistical post-processing. They interpolate out of the grid for each individual stations where you have latitude, longitude, altitude, orography. They interpolate the values, and now on a 48-hour lead time, they want to forecast just the temperature for the next day. And this post-processing is necessary to deal with systematic errors. With the best method on the used data set, using the years 2007 until 2015 for training and 2016 for testing. With the best method so far, people could reach a CRPS of 0.81. So what they now used, because we learned about the CRPS from the weather forecasting people, And the weather forecasting people thought, oh, the way you train neural networks with CRPS and you use it is similar to what we do in our post-processing. So they took just the fully connected part, the mixer density network part on their data and improved it. And with this, they were able to further reduce the CRPS to a value of 0. Oh, I can't see it on my screen, 78, I think. It was a little bit lower, yes. You also can do a lot of nice things now with the data. You can use some things to project the data. Just to give you a view, you try to squeeze down the parameters of all individual stations. You project them to a 2D plane. You color based on the 2D plane. And then you can start to have an interpretation. And you see bigger cities and the Rhine Valley here in Germany have different correction terms they require. And future and ongoing work is currently, we are now using locations, we are using a compressed view of the cloud image, of the dew points, of the temperature, of the pressure regime, to sort of understand what is the overall weather regime in Europe, condense it out of the complex things. And current experiments indicate that we even can go to a CRPS of 0.76. So we are further improving just by having this collaboration between people in astronomy and people in weather forecasting and statistics. And now, not to blast the whole thing, coming to the conclusion, probabilistic photometric redshift regression is something essential in astronomy because it's essential for cosmology. And we need to do it in order to understand the early universe. But what we were lacking at the beginning was a proper evaluation. And here, discussion and input from statisticians who were dealing with uncertainties in weather forecasting helped us a lot. So we used then, and we were the first actually, to use the CRPS for the evaluation and as loss function for training of a deep convolutional neural network, of a neural network in general. Now, a lot of other people use it in biomedical applications because it's really something like a truth serum enforcing that you're not lying about your uncertainties. Then we had everything and we gave our code away to the statisticians and they used it to now do post-processing for the weather forecast simulations. So just to conclude, uncertainty is necessary to be more precise. It seems a little bit awkward, but by giving uncertainties, people can be more precise in how much value they put to certain estimates and certain values. Choosing the right score for training and evaluation is essential because this allows you to put a focus on specific things you are interested in. And the root mean square error, even though we constantly use it, is not the best way to do it. Data science is very interdisciplinary, so let's learn from each other. So I would like to acknowledge Antonio Di Santo, Sebastian Lerck, and Tilman Gneiting. Those are the ones at HITS we were working with, and most of the work on the astronomy side originates from Antonio Di Santo's PhD thesis. So many thanks for the fruitful collaboration, and thanks for your attention. And now I just need to get my sound running, and I still do not understand why I can't hear anything.
So if people have questions,
Hello,
they can.
hello.
Hello?
Can someone say something?
I'm talking. This is Jessica. Can you hear me?
Yes, I can hear you. Yeah.
Oh, good. So if people have questions, we'll take a couple minutes for them. We've got 5 minutes till we start the next session.
Yeah, I'm so sorry for the.
So anyway, you can raise your hand on Zoom. I'm watching there, or you can ask on Discord. Let's see. Mark Taylor asks, as a result, PDF is harder to work with than a mean plus standard deviation. Are astronomers well set up to deal with model outputs in this form?
Mark, yeah, thanks. This is a really good question. So in principle, in Trieste, I presented a package to deal with those things for some simple aspects of that. But what we really have to think about is to change our databases. In a database, storing a simple mean and a standard deviation value is easy, but perhaps we can find nice representations to be stored in a database and adding that to ADQL to accelerate our queries so that we can phrase a query and saying, give me all quasars with a redshift between 3 and 4 with a probability of more than 95%. So this is really something we have to work on, because machine learning easily allows you to produce something like a probability. But in the end, it's up to us to make use of it. And so far, I figured out a lot of the uncertainties that are measurement errors that are already available in surveys is just ignored. And people don't treat it. They just treat it to cut out certain values. And I think we really have to work on that. Yes.
Okay. Peter Toybin has a question. You could. I'm unmuting.
Okay. Can you?
Yeah.
Yes, I put it in the Q&A, but the question is, can we see the slide again about the CRPS definition?
Give me a second. After I'm on my third computer.
Uh-oh.
Yeah, it's really the third backup computer, and I'm happy I set up so many backups. Yes. Okay, no, I need to share the screen still.
Well, I find it very interesting because we are struggling with the same question of comparing things, and we also discarded RMS and we're trying to do something else. So that's interesting. That I want to have a closer look at that.
There you go. Do you see it?
Yeah.
It's the integral over the Bria score, if you're familiar with this one. And it's in principle, as I try to visually explain, you take the cumulative distributive function of the true redshift. This is a Heaviside step function. It's 0 before the true value, and then it immediately jumps to 1 because it's a point estimate, a point value. And then you take the cumulative distributive function of your prediction of your PDF. And if you compare both with each other, it's just the surface area between both functions. Peter, does it help?
Yeah, okay. No, thank you. Thank you. Thank you.
Okay, I have one more question from the Q&A. Alex Meshernikov asks, what about point estimates in DNN and random forest models? Did you compare them?
What means comparing? So if you take a point estimate, the point estimate doesn't allow you to do a lot of different things. So if you have a probability density function, you can automatically exclude from a further analysis those where you can't clearly give an answer, those sources where you would have a multimodality. With a single value being predicted, you can't compare it. Of course, you can take the PDFs and calculate something like the root mean square error on it. But as I try to visually explain, those are scores that don't tell you a lot about the shape of your prediction. So it's always possible to take a PDF and condense it to a mean value and then compare it. But the idea behind the PDF is to give an honest answer about where your uncertainties are, to make you more precise in your answers. And given the multimodalities, a single answer can't be a correct answer because it's not capturing the problem.
Okay, I think we should go on since it's now 12:45, but that's fine. We got to answer all the questions that were outstanding, I think.
Yeah.
So we'll move on to the first talk in the session. So thank you very much.
Yeah, thanks again for your patience getting everything running.